Up to this point, we've kind of looked at the progression of the atomic model, starting with the Dalton model, a billiard ball model, and working our way up to the quantum model, or the electron cloud model. Ever since Rutherford discovered that positively charged nucleus using the gold foil experiment, there's always been interest to find out, well, what else is there? Like, they want to dig deeper into the nucleus. The problem is that we know that there's this strong nuclear force that's going to bind all the protons and neutrons together. And on that femtometer scale, that strong force is the strongest of our four fundamental forces. And we want to be able to get past that. In order to do this, we need a lot of energy. Over the years, there's been crude particle accelerators that have been developed, but to date, our largest and most powerful particle accelerator is the Large Hadron Collider that was built by the Conseil Européen de la Recherche Nucléaire for a cost of, at the time, about 7.5 billion euros. So it was expensive, but the cost depends how you want to think about it. I would say, from a scientific perspective and what we've uncovered in particle physics, it was worth the cost. And I think the true value of it will be seen much later. So we can't think about the cost in present time. We have to look at how that impacts us later. But the Large Hadron Collider, it has a circumference of 27 kilometers. It runs underneath the ground in France and Switzerland. And it could generate particle beams up to 6.0 electron volts. So with the two particle beams kind of going around and smashing into each other, we actually get a combined energy of about 13 tera electron volts. So that is quite significant to allow us to sort of penetrate the nucleus and sort of delve a little bit deeper. And over time, we've kind of seen like how that energy requirement is necessary to increase in order to see a little bit more into matter. We know that for a hydrogen atom, if you'd like to ionize it and strip out the electron, you need about 13.6 electron volts of energy. And then if you increase the energy to a few hundred electron volts, you can start to see those electron shells. And then more energy, we could start to see the size of the nucleus. And then if we start to go past that, we can start to see the fundamental structure. The problem that we always have had until, sort of modern day technology in building these large particle accelerators was, well, not having it. Where can we get particles that will help us out? And in nature, we actually have great particle accelerators. And what we can find is that, well, there's actually particles that are showering us all the time. So naturally, we have these nice particles that are coming from distant supernovae and solar flares, and they're all showering down on us at this present time. And these high energy particles that are showering the atmosphere, these are known as cosmic rays. Specifically, these are primary cosmic rays. So they're made up of about 90% protons. The last little 10%, we'll say they're alpha particles. And, you get some other things scattered in there like electrons, muons, all those lovely things. Now, the great thing is those particles, when they're kind of showering up on the upper atmosphere, they have energy ranges anywhere from 100 MeV to 10 to the 14 MeV. That would be more than significant to start penetrating the structure of matter and seeing kind of deep into the nucleus. But of course, anytime we get something really good, there's always going to be a catch to it. And the catch is this: once those particles enter into the atmosphere, they're going to start colliding with molecules in our atmosphere, like all those air molecules, and they're going to lose energy. So instead of having that much energy, they're not really going to have that much energy by the time they make their way down to the Earth's surface. This also doesn't mention the fact that some of these particles that get showered in cosmic rays, especially when we have like decays, some of those decay products have a really short lifetime on the order of microseconds, so not particularly useful to us. So this is just showing kind of an example of a proton coming in and then interacting with molecules in the atmosphere, and we see all these lovely particles. So we just have a real smorgasbord of particles on this. So some of the new particles that you're going to see in there, you'll see these muons, you'll see anti-muons, you'll see different kinds of pions. So just to mention muons, because muons, if you study particle physics, they certainly come up quite a bit. They are very similar to an electron. It's a little bit heavier. It's about 207 times heavier. But the thing is, the muon, it doesn't live for very long. Electrons, well, we'll say they live forever. A muon's only got a lifetime of about 2.2 microseconds, so it's not sticking around very long. Anti-muon is the antiparticle to the muon. And then we have these pions or pi mesons. We'll talk about those a little bit more later. So we have the pi 0 meson, the pi plus meson, and the pi minus meson. But that's just the tip of the iceberg. Those are some new particles, and we're going to find that in the 20th century, the number of particles that discovered absolutely skyrocketed. And to date, we have about 300, at least 300 known particles. So we have quite a big collection of them. This collection of particles, we give it kind of a cute little name. We call this the particle zoo. We're not going to look at all 300 particles. We couldn't possibly do that. But there are certain particles that are of special interest to us, and we will delve into those in a bit more depth.